Hey Kim, today we're going to be doing some ck12 practice. So before we get into that, figured we could do some notes on it that will kind of help you along. So we've already done a little bit notes on percent composition. This is related to the reading in ck12. If you would like more information, you can definitely read that section. So percent composition, we described on Thursday that chemists often need to know what elements are present in a compound and in what percentage, and that helps chemists basically identify different compounds. So it's used in a lot of industries and pharmaceuticals, when creating medicines and treatments, a lot of things. So a lot of application for this. The percent composition is the percent by mass of each element in a compound, and it's calculated using the equation below. So we do use mass to determine percent composition. It's not necessarily, how many atoms per molecule, it's the mass of those atoms per molecule. So we take the mass of the element that we're interested in, divide by the total mass of the compound, and multiply by 100 to find percent by mass. Now when you plug this into the calculator, remember, 100% is just like saying 1 out of 1. So whenever I type it into a calculator, I just type in 100, okay? Because this multiplication by 100, that's just to move the decimal place over 2 spaces. So I don't really use the percent sign in my calculator when I do this. At least with the calculator I use, all that it does is multiply by 1 because it's 1 out of 1, if that kind of makes sense. So here we have a sample problem that uses mass data, so data given in terms of mass. So we have a certain newly synthesized compound that contains zinc and oxygen only. When a 20-gram sample of the compound is decomposed, 16.07 grams of zinc remains. Determine the percent composition of the compound. And whenever it asks for a percent composition, usually it's asking of all elements in the compound. If it just wants to know about one element or a few elements, it would specifically list out what elements it's looking for. So the first step in this is to list our knowns and unknowns. So given the problem, we know that we have 20 grams of a sample, so that's the mass of our compound. We know that we have 16.07 grams of zinc. The mass of oxygen isn't explicitly given in the problem, so I'm including that as an unknown. We don't know the percent zinc, and we do not know the percent oxygen. For step 2, we're actually going to calculate, and there's kind of 2 parts to this calculation because we weren't given the grams of oxygen, but it's a pretty simple thing to calculate. So we're going to use subtraction to determine what mass of oxygen is in that sample. We know that it's only made of zinc and oxygen, so if we have 16.07 grams of zinc, all the other mass has to be oxygen. So we're going to take the total mass, subtract the known mass of zinc, and that will give us the grams of oxygen. So 20 minus 16.07 tells us there are 3.93 grams of oxygen. The second part of the calculation is that we're going to find the percent composition of this, so the percent of each element in the compound. So we're going to divide each element's mass by the mass of the compound to find the percent by mass. So that is like the part that we're interested in divided by the total mass of the compound. So for zinc, we have 16.07 divided by 20 multiplied by 100, giving us 80.35% zinc. This multiplication by 100 is very important. Based on the poll that we did on Thursday, seems like a few of us kind of forget to do that to calculate to percent. So you could say that it is 0.8035 zinc, okay? And that 0.835 is out of 100. So if we multiply by 100, that gives us the actual percent. So you're not done when you just divide. That gives you a decimal. To go decimal to percent, we have to remember to multiply by 100 or move that decimal place 2 spaces over. To find the percent by mass of oxygen, we take the grams of oxygen, divide it again by 20, multiply by 100, and it gives us 19.65% oxygen. There's another way we could have found the percent by oxygen, and that is taking 100%, because nothing can be made up of more than 100% of something. If we have 100% of something, that is all of something. There's no extra credit in substances, so you cannot get over 100%. So we could hypothetically take 100 and subtract 80.35, and that will give us the percent of oxygen that is in the sample, because the percents should always add up to 100, and that's a way that you can check your answer to see if it makes sense. The mass data isn't the only way we can do percent composition. We can also find percent composition using the chemical formula of a substance. Okay, so no matter how much of a substance you have, the percent composition doesn't change. It's like a recipe for that substance. All substances are going to have the same percent composition if it's the same pure substance. So the subscripts in the formula are used to calculate the mass of each element in 1 mole of the compound. So all we do is assume 1 mole of compound, and we would see, well, how many grams per mole are there of each element. Then we divide by the molar mass of the entire compound and multiply again by 100. And again, when you type this into a calculator, I never include that percent sign because sometimes the calculator interprets it the wrong way. So I just multiply by 100 and then stick the percent sign at the end. So here we have dichlorine heptoxide, which is Cl2O7. Hopefully you remember that from our nomenclature unit. Is a highly reactive compound used in some organic synthesis reactions. Calculate the percent composition of dichlorine heptoxide. So we want to know the percent of chlorine and the percent of oxygen in this compound. So step 1, we're again going to list our knowns and unknowns. In 1 mole of Cl2O7, we have 2 times 35.45, which equals 70.90 grams of chlorine. Where did this 35.45 come from? It's the molar mass that's found on the periodic table. I multiply it by 2 because in the chemical formula for dichlorine heptoxide, we have 2 chlorine. I know that the mass of oxygen in 1 mole of dichlorine heptoxide is equal to 7 times 16, the molar mass of oxygen. And that gives me 112.00 grams of oxygen. We know that the molar mass of the entire compound is 182.90 grams per mole. You can find that just by adding together these two, because that's literally how you find it. You could just go straight from the periodic table too, but then you're just doing these calculations a second time. We do not know the percent of chlorine, and we do not know the percent of oxygen. So that is what we are going to find in step 2 when we calculate. So calculate the percent by mass. We divide the mass of that element in 1 mole of the compound, that weight that we just found, by the molar mass of the compound, multiplying by 100%. Okay, so in 1 mole of dichlorine heptoxide, we had 70.90 grams of chlorine. We divide it by the total molar mass, multiply by 100, and we get 38.76% chlorine. Then for oxygen, we do the same thing with its molar mass. How many grams would be in 1 mole of a substance for oxygen? And that would be 112 over 182.9 times 100, which is 61.24%. Okay, and I'm going to add a step 3 here. Think about your answer. Does it make sense? With the question that I gave you on Thursday, what percent of the class puts mustard in their mac and cheese? I got some pretty high percents, like 25%. 25% means 1/4 of the class. Is 3 people 1/4 of the class? No. So that answer should tell you, like, okay, I did something wrong in the calculation. Let's go back and think about it again. So for percent composition, your percentages of all elements in the compound have to add up to 100%. So again, there's no extra credit in compounds. 100% is all that we can have. So the total mass of oxygen in 1 mole of dichlorine heptoxide was 112 grams, which was greater than the total mass of chlorine in 1 mole of the compound. So the percent of oxygen is and should be greater than that of chlorine if that mass is greater. Since it is, and these percentages add up to 100%, I'm pretty confident that my answer is correct. We can also kind of work backwards and determine mass from percent given the sample. So percent composition can also be used to determine the mass of a certain element that is contained in any sample of a compound. So in the previous example that we just did, we found the percent composition of dichlorine heptoxide using the chemical formula. okay? No matter what sample, if I have 1 gram of a sample, 1,000 grams of a sample, or a whole truckload of a sample, 38.76% of that sample is always going to be chlorine, and 61.24% is always going to be oxygen. So if we want to know the mass of chlorine and oxygen that's present in a sample of 12.5 grams, we can determine the mass of each element simply by multiplying the percent by the total mass. So I'm going to take my 12.5 gram sample and multiply it by 38.76% to find the mass of chlorine. Now again, in my calculator, I always like to just convert to decimal for multiplying. So that's why I multiply by 0.3876 to find the grams of chlorine in that sample. I do the same thing for oxygen. 12.5 times 0.6124, I get 7.65 grams of oxygen. Now I can think about it. The sum of the two masses is equal to 12.50 grams, the mass of the sample size. That makes sense. If I add together the 2 grams, they should add up to 100%, which will give me the total mass of the compound, 12.50. Now, if you add them up and you get 12.51 grams, remember, because of sig figs, this last decimal that's listed is estimated. And so since 12.51, that last digit is the only one that's different, and it's pretty dang close to 12.5, I would say, yes, that answer still makes sense because of sig figs, rounding, and estimation, okay? So review for this unit, questions to kind of think about. What's the formula for calculating percent composition? And we kind of use 2 different formulas, but it's the same idea overall. Percent, no matter what you're finding for it, is always the same idea. We have part over whole, okay? What information do you need to calculate percent composition by mass? Again, you can have different things. We did different examples here, given different data. What do subscripts in a chemical formula tell you? And that's kind of review from previous units when you're naming compounds. What does that subscript tell me? Okay, so that is the notes for the 10.10 unit on ck12. Next up, you will be doing those practice problems, and if you don't finish them, you can finish them for homework. But that is all that we're doing for the rest of the day. Okay, I will be on our class Google Meets if you encounter a problem that you're not sure how to do it or why your answer's popping up as wrong or anything like that. Okay, have a wonderful day.